Okay, we're given an equation for y and an equation for x. We can identify the equation for y as a uniform acceleration equation. 10 meters, constant, that's our x naught. 8 meters per second times t, that's v naught times t, minus 5 meters per second squared times t squared. Acceleration of negative 10 meters per second. And you should think very hard about why those quantities are as I just described them. Okay, now x is 4 meters plus 5 meters per second times t. And we're told that y reaches its maximum after 8/10 of a second. Okay, so y reaches its maximum at t equals 0.8 seconds. What do we determine from this? Well, y is going to reach its maximum when the first derivative is 0. Okay, so that means y prime is 0 at t equals 0.8 seconds. Many ways to interpret that. If things moving upward, it reaches its maximum height when it reaches 0 velocity. Velocity being the derivative of your position, that means the derivative of the position would be 0 at that point. Then, having seen this, it follows that at t equals, at the time when y reaches its maximum, x is 8 meters because the maximum occurs at 0.8 seconds. 0.8 seconds times 5 meters per second is 4 meters. Add that to 4 meters, we get 8 meters. Now we're asked to eliminate t from the two equations to get y as a function of x. Okay? And at this point, I said, does any of this seem familiar to you? Because everybody in the course is also taking vector calculus, and we had a couple of review sections while we were working through the actual course that addressed parametric equations. Okay, and you were asked if you had this to eliminate the parameter from parametric equations. So your context here is the same as the context for the vector calculus. And I digressed, and I'm going to digress right now just to mention that you're seeing things in vector calculus that you're seeing in physics. They might look a little different. It's part of a different course, so why should they be the same? Well, you've got to pay attention and see that, okay? And also, you're taking a dynamics course. Of all things, dynamics is directly related to all this. You're doing all this in dynamics. You're doing the same thing in 3 courses at the same time, and you're going to find that. And you need to be alert to that, and you need to recognize when that happens, because then you have to do less work to master the 3 courses. Now, each course goes off in different directions. There's a lot of stuff that's done in vector calculus that isn't going to be relevant in your first semester physics, although almost all of it is going to be relevant in second semester. And dynamics goes off into a lot of special cases, a lot of modifications that we don't address in physics because we're trying to do a lot more in physics than just dynamics, kinematics, and so forth, okay? But at this stage of the course, and for quite a while during these courses, you'll be doing stuff in one course that's directly applicable to something that comes just a little later or maybe even at the same time in another course, and you've got to be alert to that. So all we're doing is we're eliminating the parameter to get y in terms of x. So the way we do that, well, I just solved this equation for t. I got this. Plug that up here, I get this. And that's very straightforward. Here it is where t was. Here it is where t was. Now we've got to expand the square and all that stuff. And when we get done doing all the arithmetic, we get this equation. What kind of an equation is this? Y is a quadratic function of x, meaning the graph is a parabola. So I could say this is a quadratic function, so our graph is a parabola, meaning that, okay, when t is 0, y is 10 meters, so let's just put an origin here. And when t is 0, x is 4 meters. So we have the point 4 meters (10 meters) on our graph. And if you let x equal 4, you're going to get y equals 4 meters. You're going to get y equals 10. Yeah, okay. I was looking at my units, making sure they were right. Okay, and let me digress to talk about the units. Why do we have a meter in the denominator here? Well, because that's the way it came out when we wrote all our units and worked the units through. Does it make sense we should have a meter in the denominator here? Yeah. If we don't, we're in big trouble because y is measured in meters, and x squared over 5 meters should be measured in meters. X squared is in meters squared since x is in meters. If we didn't have a meter here, then the unit of this expression would not be meters, and it wouldn't be compatible with this expression. You couldn't have them both in the same equation as terms in the same equation. Okay? So you have to have the meter there. And of course you do get the meter if you just do the algebra of the units. So looking at this, you determine whether it's dimensionally consistent. Are the units of this term compatible with the units of this term? Yes, they are. This term would give you meters if x is in meters, and this term would give you meters, assuming everything's measured in meters. And 48/5 x, is that in meters? Well, yeah, x is in meters, so 48/5 x is in meters, so that's compatible with the units of this term and this term. All terms have to have the same units. And what about 2/5 meter? Well, it's obvious that 2/5 of a meter has units of meters. So all these terms have units of meters, y has units of meters, so that we're dimensionally consistent, okay? Very important to check that. If you don't come out dimensionally consistent, there are two possibilities. One is you screwed up your units, and you shouldn't be screwing up units because it's always fairly easy, but still easy to screw up. The more likely thing, though, once you're decent at units, is you screwed up your algebra someplace, or there's something wrong in the way you conceptualize the problem. So you always have to do the units. And of course, I'm always going to expect to see the units, and I'm going to penalize if they aren't there. Okay, and for that reason, it's for your own good. Okay. Now, on this graph of y versus x, we know that the graph goes through here. We know that the graph reaches its peak when x equals 8 meters. Okay, so when x is 8 meters, we're going to be at our highest point. We could solve this equation to see for what value of x y equals 0. And looking at this equation, a little bit disturbing. If I do negative b over 2a, I don't get 8 meters, but I know that the peak ought to appear here, so there could be something wrong with this solution, so please check it out. It's going to be much like this, but if I do the negative b over 2a, I get x equals 24 meters. As I say, that's disturbing, but there might be something wrong with my arithmetic here, despite the fact that my units all came out the same. Okay, in any case, the graph is going to be a parabola. It's going to peak at 8 meters, so it's going to look something like this. But I don't know exactly how high or low that peak will be. I can put 0.8 seconds in and solve for y and see how high it'll be. Then I got a real good idea of the parabola. I can set this equation equal to 0 and see where the graph would intersect the x-axis. Okay? If I'm asked when this thing lands on a platform that's at y coordinate 3 meters, well, I could say, okay, here's 3 meters, so I'm trying to find when the thing is here. And you just adjust the functions to make it so. Okay, now, another question that was asked, what's the direction of motion at a given instant? So if I've got an instant here, and this is in terms of t, there's some time t when it would be here, direction of motion is tangent to the curve. What would be the direction of motion? Well, if you're given the value of t, the velocity is what? Well, the velocity vector is the derivative of the x, which is the velocity in the x direction, times the I vector, plus the velocity in the y direction, the derivative of your y function, times the j vector. So the velocity is x prime t plus y times I plus y prime of t times j, and taking the derivatives and so forth, we find that the velocity vector is 5 meters per second times I plus negative 10 meters per second squared times t plus 8 meters per second squared per second. Okay, just the derivative of what we get up here. Okay, that gives you the velocity vector, the time dependence of the velocity vector as a function of time. If we wanted the velocity vector as a function of x, well, time is x minus 4 meters over 5 meters per second. Assuming I solved this correctly, and I think I did. So we could plug that in for t here. That's the only place t occurs. And now we have the velocity as a function of x. Okay, what's the speed? The speed is the magnitude of the velocity. And reiterating what I said before, we did this on, I think, about the first day of our vector calculus course. So you want to review that, but this is just one simple application of vector calculus. If you want to find the distance along the arc between two times, you integrate the magnitude of your velocity vector with respect to time. And of course you could get the arc length from this function as well if you're given two positions x. You really wouldn't be too interested in the arc length of this parabola, but there are other cases where you might be. The other thing is this is a projectile, okay? Because this is the motion you would have in a gravitational field where the acceleration is 10 meters per second squared downward. Now, if you want to use 9.8, then that would be 4.9 instead of 5. Okay, so your y motion is just uniformly accelerated motion. Your x motion is just uniform velocity motion.